Welcome to an intro to kinematics, where we will discuss one-dimensional motion. Kinematics deals with the study of motion of various objects and particles. For this video and most videos onward, we will have a constant acceleration. For simplicity, many problems assume no air resistance, no particle-like motion, and absence of any other minor irregularities. This video will introduce a lot of new content, so if you feel that it is too fast or too slow, please comment your preference in the comment section. So our first new word is displacement. Displacement is the distance from your final position to the initial position. So if I walk 3 steps to the right, then my displacement would be 3 steps. This is not to be confused with the distance traveled. So the distance traveled is the total distance traveled in getting to the final position, where the displacement is only the difference between the initial position and the final position. If that's confusing for you right now, we'll clear it up later in a later slide. The standard unit for this is meters, shortened as m. Our next word is velocity, which is displacement per unit time. Average velocity is the velocity over a specified interval of time, and while instantaneous velocity is the velocity at an instant, so that's an infinitesimally small interval of time. This may all seem confusing to you right now, but we will review all of this later. The standard unit for this is meters per second, shortened as m/s. Our final new word is acceleration. Acceleration is the change in velocity per unit time. The average acceleration is acceleration over a specified interval of time, similar to average velocity, and instantaneous acceleration is acceleration at an instant. The standard unit for this is meters per second, or meters per second squared. So something to note here is that although in everyday life we use speed and velocity interchangeably, they're actually not the same thing in physics. So velocity has a direction and speed does not. So that means velocity would specify a value and a direction. So I could, saying I'm moving at 3 meters per second north, that's velocity. But my speed would just be 3 meters per second. In one dimension, this means velocity can be negative. So if you define right as the positive direction, then a negative velocity would just mean you're moving left. Also, something very important here is that speed is the distance traveled over time, where the velocity is displacement over time. And like I explained in the last slide, those are not the same thing. If an object travels from point A to point B and back to the original point A, then travels to another point C, then find the speed, displacement, distance traveled, and velocity of the object. So let's see our information given. Point C is 2 meters to the left of point A. So let's draw a diagram here. So this is 2 meters. Sorry. We also have point B, which is 4 meters to the right of point A. The time for this to occur is 3 seconds. So first, let's find the displacement. Since it goes from A to B, that's 4. Then it goes back to A. Then it goes to C. So that's 4 plus 4 plus 2. Sorry, that's not displacement. This is distance traveled. That's 10 meters. And now for displacement, all we have to do is we know that the final position is C and the initial position is A, and the distance between those is just 2 meters. So the displacement is 2 meters. Now we need to know the speed of the object. Since it took 3 seconds, that would be the distance traveled over the time. So that's 10 over 3, which is 3.3 meters per second. But the velocity is the displacement over time, not the distance traveled over time. So velocity would be 2 over 3, which is 0.67. Let's keep it consistent here. I'll just put the bar. Yeah. So now we have all the values and we're done. Now we will discuss the relationship between displacement, velocity, acceleration, and time. So we have the definition of average velocity, which means which is the change in x, so the change in position, over the change in time. So the change in x is the same as the final position minus the initial position. So if we plug that in, and we have initial time as 0, so that means the change in time is just time. Then the average velocity is the same as the quantity of final position minus initial position all over time. Then we can solve for x, and we get this expression right here. So that's x equals initial position plus average velocity times time. Yes, this is a linear relationship, so position relates linearly to velocity. But what if velocity isn't constant? This is where acceleration comes in. Average acceleration is the change in velocity over the change in time. And similar to average velocity, this is the same as the final velocity minus initial velocity all over time. Using this, we can solve for final velocity, which equals initial velocity plus acceleration times time. If we rewrite this in this expression, then we know, and this quantity is the same as average velocity. So then we can plug in average velocity and substitute the equation we got last slide in order to get this final equation. So the derivation of this formula is important, but these are the equations that can be derived from the information we already know. These are all very important and should be memorized. Keep in mind, though, that these are only applicable when acceleration is constant. To solve a problem, typically out of position, velocity, acceleration, and time, you are given 3 knowns and are asked to solve for the 4th. However, it's not always clear what your 3 knowns are. Our intuition tells us that heavier objects tend to fall faster in freefall than lighter objects. But this is only true when we put into account air resistance and other minor forces. And if we don't put those into account, then yes, all objects accelerate at the same rate in freefall. So this does mean there is a constant acceleration, which is denoted by g, or which is equal to 9.8 meters per second squared. Now we will look at some examples of kinematics problems. Let's say you're driving at 65 kilometers per hour, and you suddenly see a car in front of you and press your brakes. How long will it take for your car to stop, assuming that the brakes decelerate the car at a rate of 4 meters per second? Actually, this should be 4 meters per second squared, since it's acceleration. So the first thing we see is that these units are different. So 65 kilometers per hour, we want to convert that into meters per second. So this is how you do that. 65 kilometers per hour. And now you can multiply this by the amount, you know that there are 1,000 meters in 1 kilometer. And then you want to convert this hours into seconds. So first you know that there's 1 hour per 60 minutes. And there's 1 minute per 60 seconds. So multiplying all these together, these cancel out. So finally you get 65,000 over 3,600 kilometers per hour. It's meters per second. And that turns out to be 18.06. So now that we know the initial speed, we have to find the two other knowns. So the acceleration is negative since it's decelerating. So that would be negative 4 meters per second squared. And the final known is the final velocity, since we're finding when it stops. So that means the final velocity is 0. Since we have these three knowns, we can now plug this into an equation and get an answer. Now it's just which equation do we use? If we look through the equations, we see one of them is final velocity equals initial velocity plus acceleration times time. So plugging these in, you get 0 equals and now you just solve for t. Plug that into a calculator. And you get 4.52 seconds. Okay, now for number 2. Assuming the same situation as above, how far will you move in that time? So we know all these variables: velocity, acceleration, final velocity, and time. Now how do we find the displacement, that's change in x? So we can use any other equation. One convenient one is v final plus v initial over 2 times time. So if we plug that in and we solve for change in x, that equals 40.82 meters. Okay, now let's clear this. Okay, number 3. If a person drops a penny from a height of 950 meters, how long will it take for it to hit the ground? And what will the velocity of the penny be the instant it hits the ground? So we're given a lot of information here, so the first thing we want to do is write it down. The height is 950 meters, and that's essentially the displacement. So that's change in x. What else do we know? The velocity, the acceleration is just g, since it's in free fall, and we know that's 9.8 meters per second squared. And since he drops it from a stopped motion, and since the person drops it from and since the person drops it from a complete stop, the initial velocity is just 0. And finally, we're trying to find the final velocity, since it's asking for the velocity when it hits the ground. So let's look at our equations again. And for this one, it would be, the best one would be v squared equals initial v squared plus 2a times change in x. So we can just plug in our values here. And we finally get 136.46 meters per second. So as you can see, kinematics problems are pretty easy as long as you stay organized and write down all your work. The hardest part is mostly identifying the variables and choosing an equation. Once you do that, it should be a piece of cake. Thanks for watching. Please leave a like and subscribe, and we hope to see you next week.